The following video is on classifying discontinuities. There are three types of discontinuities that we'll study in this video. Removable discontinuities, which look like holes, jump discontinuities, and infinite discontinuities, which usually will be vertical asymptotes. So let's look at some graphs that are not continuous. Notice that on each of the graphs at the value x equals a, we'll have to pick up our pencil in order to keep drawing as we move past a. So in the first two functions, we see that we have a removable discontinuity, and remember these look like holes in the graph. In the third function, we have a jump because as I'm moving from the left of a to the right of a, I have to jump to keep moving along the function. And the fourth one, I have a vertical asymptote. Notice that as we approach a from above and below, the y value is going to infinity. So let's spend a little time looking at each of these, and we'll start with removable discontinuities, which remember look like holes. We'll say that a function f of x has a removable discontinuity at x equals a if the limit as x goes to a of f of x exists, but does not equal f of a. So the two examples from our previous page, we see that the limit as x goes to a of f of x in both of these cases is L, but in the first case, f of a doesn't exist. There's no solid dot above a. In the second case, we see that f of a actually equals b, which is not the same number as L. Usually removable discontinuities occur in piecewise functions or in rational functions where we can cancel the x minus a term from the top and the bottom. Let's look at some examples. So here we have the function f of x equals x minus 1 over x squared minus 1, which I can factor out to x minus 1 over x plus 1 times x minus 1. And notice that I can cancel x minus 1 out of the top and the bottom. So if we take the limit as x goes to 1, we cancel the x minus 1 term out of the top and the bottom, and I'm left with the limit as x goes to 1 over x plus 1, which is 1 over 2. So the limit does exist, it goes to 1/2, but f of 1 does not exist because if we tried to plug in x equals 1, we would have the denominator equaling 0 and the world would explode. So we have a removable discontinuity at x equals 1. The graph of the function looks something like this. Notice that as x goes to 1, the limit is going to 1/2, but at x equals 1 we have a hole, and that's how we know we have a removable discontinuity. Let's look at another example. Here we have f of x equals x squared if x is not 0 and 1 if x is 0. And we're worried about x equals 0 because that's where we're gluing two functions together. So we take the limit as x goes to 0 of f of x, and we see that we get 0, but we see that if we try plugging in f of 0, we end up with 1. So the limit does not equal f of 0, and so once again we have a removable discontinuity. Let's look at a graph of this. We have everywhere that's not equal to 0, we have the graph looking like x squared, and at x equals 0 we have the y value as 1. So notice that we have a hole at x equals 0, so we have a removable discontinuity. Next, let's talk about jump discontinuities. A function f of x has a jump discontinuity at x equals a if the limit as x goes to a from below and the limit as x goes to a from above exist but are not equal to each other. Jump discontinuities typically occur in piecewise functions or rational functions with absolute values. So once again, we have a picture of a jump discontinuity. As I approach a from below, the y value is going to b, and if I approach a from above, the y value is going to c. Here's an example. F of x equals x squared if x is less than 0, and 1 if x is greater than or equal to 0. We're worried about x equals 0 because that's where we're gluing two functions together. The limit as x goes to 0 from below of f of x is, let's say we're going to use the x squared function, so we can do direct substitution and get 0. As we approach 0 from above, we're going to use the 1, so we get 1. So notice that the limits from above and below don't agree, so that means that we have a jump discontinuity. We can look at a graph of this function and notice that as I approach x equals 0, from below I'm going to 0, from above I'm going to 1, so if I were to walk along this function I would have to jump at x equals 0. Here's another example. F of x equals the absolute value of x over x. We're worried about x equals 0 because that would make the world explode. The denominator is 0. If we take the limit as x goes to 0 from below, we get negative 1. And if we take the limit as x goes to 0 from above, we get positive 1. This is an example that we've spent a lot of time looking at. So the limit from above and below don't agree, so we have a jump discontinuity at x equals 0. Looking at a graph, we see that as we were to approach 0 from below, we would have to then jump to continue everywhere above 0. The last type of discontinuity is called a vertical asymptote. A function f of x has a vertical asymptote at x equals a if the limit as x goes to a from above or below goes to positive or negative infinity. And once again, the example that we saw at the beginning, as we approached a from above, it was going to negative infinity, and from below, it was going to positive infinity. But really, only one side is required to be infinite in order to say that we have a vertical asymptote. Vertical asymptotes are usually seen with rational functions, trig functions, or natural logs. Let's look at an example. F of x equals the natural log of x minus 2. We're worried about x equals 2 because we know that the natural log of 0 is undefined. The limit as x goes to 2 from above goes to negative infinity, so there's a vertical asymptote at x equals 2. The graph of the function looks something like this, and remember that the natural log is not defined for negative inputs. So if x is anything less than 2, we'll end up with a negative input for natural log. So notice that the graph doesn't even exist on the left side of the asymptote. Looking at another example, this is the same function we saw earlier, f of x equals x minus 1 over x squared minus 1. And earlier we saw that at x equals 1, we had a removable discontinuity. But now we'd like to see what happens at x equals negative 1. The limit as x goes to negative 1 from above. Let's see, so we're going to simplify it to 1 over x plus 1. But when I try to plug in negative 1, I get 1 over a very tiny positive number. So that goes to positive infinity. If we do the same thing from below, we'll also get an infinite number. But this is enough to show that we have a vertical asymptote at x equals -1. And we saw the graph earlier. As we approach -1 from above, we're going to positive infinity. As we approach -1 from below, we go to negative infinity.